So in this video we are going to look at statistics and tests that can be done in Maxima using the Inference package or the Inference result package. So the first thing we have to do is load Inference result. And inference result is a structure, it is an object that is predefined in Maxima. If you did R has a similar structure when it comes to handling statistical objects. So having an inference result object would standardize across multiple statistical tests, because most statistical tests follow a similar structure. So let's start with a very simple test, which is a test for mean. So I'm going to call it data. So that is my data variable, and those are the observations that I have. And I would want to test to see if is the true mean 5. That is our test. So the function that we have is simply test mean. We pass in the data. We have to specify a confidence level. So the argument here is conf level, and that would be 0.95. And we have to specify the alternative for the test. So we know a statistical test could either be right-tailed, left-tailed, or two-tailed. So here we simply have greater, less than, or two-tailed. I believe it is equal. So I'm going to go with greater. And the mean that we are testing for is 5. And that's what I get. So that result that you see there is what we call the inference result object. So I'm going to define a variable, and I'm going to do the same thing and alternative equals less and mean equals 5. So I'm going for a left tail test instead of a right tail test. And this time I have saved the test results to the variable mean underscore test. Mean underscore test now is an object, and it is an object of the type inference result. So here I see a whole lot of output values. So what if I want to know the items in the object that was returned? So I could simply type items underscore inference and go for mean test. So that is the name of the variable. I know that that particular variable is an inference result object. So when I do items underscore inference, it is going to tell me all the values that are stored. So you can see the estimate of the mean that we get from the sample, the confidence level that we supplied, the confidence interval, the method that was used, the hypothesis that we have, the value of the test statistic, the distribution that we use, and the p-value. So if you don't know these terms, I would strongly recommend that you go back and look at statistical inference and hypothesis testing. Suppose I want to access a single value from the test that I just performed. For instance, I just want to know the value of the test statistic. Command here is take inference, and I know the values or the different elements that are inside the inference object, so I'm just going to go for conf interval, and the name of the object is mean underscore test, and it gives me just the confidence interval. So having things defined as an inference object simply makes things easier for us in terms of creating different test values. So another test that we have is a difference in means. It's a two-sample test. So every single inference object that is defined as a statistical test is likely to have all of those values. As I mentioned, defining it as an inference object has or introduces flexibility for us to have a standard structure for all statistical tests. So let's say I want to create two different samples. So I'm going to have a sample X and then I'm going to have sample Y. So I'm going to say data underscore X. And I'm going to have the values 0.1 to 1.5, negative 2, 3, negative 4, 5, 1, 2, 3. And I'm going to define data underscore Y as 1, minus 1, 0, 1, 9, 6, 5, 2, 1. And now I want to use a two-sample test. A two-sample test is test means difference I'm going to save that to a variable toSamp, and I'm going to pass the first list, I'm going to pass the second list, and I'm going to specify an alternative, and I'm going to go for two-sided. In other words, I want to test to see if the first sample mean is equal to the second sample mean. And those are the values that I get. So I have the difference estimate, so the difference between the two sample means is negative 0.506, and the definition of the test is right here. The null is that the first mean is equal to the second mean. The alternative is that they're not equal, and the test statistic is that value, and p-value is 0.6607. So here there is a test called a Welsh approximation, which computes degrees of freedom using a formula, which is why we have a decimal value. So if I want to access a specific object, for instance, I want to access the p-value, And I could simply say take inference to sum and p-value. I believe it's underscore. So that would be the p-value of the test, which is right over there. And I can get that by using take inference. So, we have a data which is the biomed data, and I read it as a matrix, and I'm going to save it as BM data. So that is a biomed data, and it has 5 different columns, and I want to see if the means of, say, the first column, I don't know what these columns are, but if you Google it, you'll know what they are. So the objective here is I want to see if the mean of the group A, or for the values in column 1, is the same as the mean of group B, which is right over there. So how would we go about doing this? So there is an option called subsample, and I'm going to say subsample BM data, the first column of BM data must equal B. I think I'm doing this right. Let's see if it gives me the value that I want. No. Should work. What am I? Perhaps I should specify it as a lambda function. So I'm going to pass the original data set, which is BM data. I'm going to define a lambda function, x, and I'm going to specify x1, which is the first column, equals b. Still nothing. Perhaps it's not a character. there we go. So so I have split all the values that correspond to the group B, and that is a matrix. Now I want to do the same for group A, but this time I want to subsample it using a function. So I could define g of y, y of 1 equals a. So I'm going to create a new variable for group A. Going to subsample the original data, BM data, and this time I'm simply going to pass in the function that I defined. Instead of putting in a lambda function here, I'm simply going to pass the function that I defined, and that gives me all the values corresponding to group A. So I have a sample for group B, I have a sample for group A. Now I simply want to pick the first column, so I'm going to go for test underscore means underscore difference. BM data underscore A, I'm picking the second column, and BM data underscore B, I am going to pick the second column. I'll call that BM test. And the reference value, I'm going to specify it as 0 because we want to see if the means are the same. So I'm going to do a test for equality. So alternative would be two-sided. There is an object called equal variances. This is a logical value. I could specify true or false, and I'm going to specify true, even though I do not know if the variances are the same for both the samples. And that's what I end up getting. Doesn't look very pretty here. So you can see it's doing a whole lot of calculation using A and B. So let's see what we have in our BM data underscore A of 2. So you can see it is actually picking the first row and not the first column. So we want to get the first column of the matrix, so perhaps we could do call and that is going to pick up the second column. So I am going to go back here and specify the second column of group A, and the second column of group B, and those are the data values. And if I did take inference, and if I wanted to find the p-value, that is the p-value for the test. In other words, the variance of the first group, the mean of the first group is not equal to the mean of the second group, and that would be our conclusion. So there are plenty of other tests that we can do, and they all sort of follow the same structure. For example, let's say I want to test the proportion for the second or the third column, and I want to ask the question if the proportion of values in column number 5 for group A is greater than 0.5 if the condition being the values are less than 200. In other words, I want to find the number of items or number of values in column 5 of BM data that are greater than 200, and the next thing I want to do, I'll call that $200. I'll say 4 group A, and the question we want to ask, the proportion of values that are greater than 200 in group A is less than 0.6. So that is something we want to test. So in order to do this test, we simply have to do a test for proportion, and a test for proportion can be done using the function test underscore proportion, and it takes two values x and n. So we need to find the value of n, then we need to find the value of x. What is the value of n? N would be the total number of observations in group A, and the value of x would be the number of observations in group A that are greater than 200. So I'm going to do a subsample. I'll call it BM data 200, subsample BM data, and lambda function, I'm going to specify I want group A and I would like to have column 5 to be greater than 200. Maybe it is and. weird. Than 200. Okay, that gives us all the values of A. I believe it's and. I was doing the wrong column. I was doing column number 5, and none of the values there are greater than 200. That's why. So it has to be column number 6. And those are the values we have in total. So that is BM data underscore 200. It picks all the values of group A so that column number 6, the observations are greater than 200. So So I'm going to look at the length of the subsampled data. In other words, we have group A, and in group A we picked column number 6. And what is column number 6? That would be the number of observations greater than 200, and it seems like we have 28 of them. What is the total number of group A observations? So I'm going to define that as n, column, the original data set, BM data, and it doesn't matter which column that we pick. Has to be BM data underscore A, and I'm going to pick the first column, and that would be 38. So the number of observations in group A, number of observations in column 6 of group A that are greater than 200 is 28. The total number of observations in group A is 35. The test that we want to perform is test underscore proportion, and we'd like to know if the proportion of observations are greater than 200 in column 6 for group A is less than, where did I type it? The proportion is less than 0.6. So test underscore proportion, we have the x value, we have the n value, and we have to specify proportion, which would be 0.6, and the alternative is less. What is so weird here? Did I not evaluate this? 28, 35. That worked. Yeah, it should work. So what we have is a test for proportion. The sample proportion is 0.8, and the test that we're trying to perform is to see if the proportion is less than 0.6, and the p-value is 0.9965. In other words, we don't reject the null, so the proportion is actually greater than 0.6, which is quite obvious from looking at the sample proportion. Excuse me. So oftentimes we would want to read a data file and get data from the data file and perform some sort of a test. So what I have here is a CSV file that I have defined as temp.csv. And it has a bunch of values in column A and a bunch of values in column B. And I want to read this file. One of the simplest ways to access a file is using something called a connection. You open a connection and you close the connection. This goes back to compiler languages such as C, Fortran and so forth, and of course Lisp. So I am going to call connect as my connection, and I'm going to say open R temp.csv, and it tells us we've opened a stream named connect, and that particular stream is going to access the file temp.csv. Once we do that, we can open connect read underscore matrix connect, and that takes in all the values. Now I'm going to save that to a variable called mat, and those are simply the values from the data file. Let me do close connect also. Let's try this again. And there we go. So if you open a connection, we have to close the connection. And if we don't close the connection, then sometimes it would result in computational issues. So now I have two columns, column 1 and column 2. Of course, there we see false, 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 and those are missing values. Now I can perform a test to see if the means are the same for column 1 and column 2. So I'm going to call mat underscore 1 as column of mat 1. It's the first column. Mat underscore 2 is the column of mat, the second column, has a bunch of false values too. I'm going to subsample mat Okay, not equal. I believe it's not equal. Let's see. I need a quick reference check here. Let's try that. It doesn't work either. Oh. Let's see if that works. Should work. Seems like there is some sort of an issue here, but I am going to try and do the test for mean difference. I'm going to pass in the first matrix. So what I was trying to do is I was trying to remove the false statements or observations that are false, but I think that test should work on its own without removing those false values, but we will see. Maybe there is a clash here. Looks like the test underscore means difference is defined for lists, and what we have is a matrix. So we may have to convert a matrix, which is a column vector, to a list. Okay, so let's try to do this. Perhaps there is an easier way to go about it, but I'm just going to do it this way. For true length of call. Ah. Okay, let's see what we have in. Okay, I have that list, but it still has as a matrix. So let's try to do this instead. We will try to read this as a list, if that would work. So what I did here is I simply read it as a list. So let's see what Matt has. So Matt now has a list, but you can see it combined everything in the file. It didn't look at column 1 and column 2 separately. So we ran into a bunch of issues here. One, we tried to read it as a matrix, but then we had issues using the matrix directly in the test underscore mean difference inference object. So I tried to read it as a list, and in this case it just forgets to combine forgets to keep them separate, the two columns separate. Let me give it one more try. There is another command called array, so let's open the connection. And let's see what Matt gives us. It gives us a Lisp array, so that's not going to work here. There is an option for a separator. I believe it's in read list. I think so. So there is a package called Numericalio, and you can look in Numericalio, and that tells us, or that gives us different options to read a file, either as a text file or as a data file or a binary data file and so forth. Let me see if I can specify a separator. I'm going to go with comma, and let's see what happens. let me try space. Let's see, temp.csv. Maybe the file format is not set properly, so let me save this as a text file. It's text CSV, and I am going to go the values are comma separated, so let's try and load this as a list. Going to specify comma, change the file name to text. So it combines everything. So let's see, we could go back to opening the file. I'm going to go, say, connect CSV, open R, temp.csv, and open connect CSV. I'm going to connect to the file. Let's try this again. Mat new. Gonna read it as a matrix. Connect CSV. Want to convert this to a list. Mat underscore list. Let me use the args command. That might work. That works, but doesn't give us separate lists. Now you may say, well, what is he trying to do here? I'm trying to get two lists so that I can pass it to the means function. So test underscore means underscore difference. When I simply passed column mat new 1 and column mat underscore new 2, it wouldn't work because it gave us an error. Oh, sorry. Right here, and it said it's a matrix, and it can't be a matrix. So it has to recognize it as a list of values. So I'm trying to convert it to a list. Let's try the loop again. Can't give up here. What's in mat new? So we're running into all kinds of issues. Finally, we ended up getting the list for mat X. I'm going to do mat Y. I'm sure there is a different way or a different approach here, but so I am going to go for another for loop. I'm going to get the temporary value here. So each row, second column. But this time, excuse me, I'm going to push only if X is a number. In other words, I don't want it to have a value of false. So if X not equal to false, I believe that is the correct logical operator, I'm going to push the value of X to mat_y. Forgot then. Okay, so my error here is with a not equal to operator. So let's see this. If x is greater than or equal to 0, or x is less than 0, we can push. Evaluate all cells. And I got mat_y. So you kind of see all kinds of problems that we encounter when we are reading a file, and it happens with many languages, but R, on the other hand, doesn't have such problems, and back then R used to have issues with reading files. It was quite difficult, and you've got to do all kinds of things, but things have developed over the years. Maxima, on the other hand, has not. So now finally I have two different lists, and I can go ahead and do my tests and be happy. So there are other tests. There are plenty of them, as I mentioned earlier. There is test for proportions, difference of proportions, variance, f-test, and whole kinds of other things. But I'm not going to get into every single one of them, because if we know one test, we could do the others, because they all follow the same structure, and that is the point of having an inference result object. So I am going to go and use mat_x and y. Alternative is less, and it worked. It took some time, but we got it to work. So that's how you read data from a file and use that data to perform a test. There is something very similar between the Maxima package, or the stats package in Maxima, and the R behavior, which is it has the inference result. Now, there is another package called distrib, and that stands for distribution, and R is meant for statistical analysis, so all of these are built in R. But in Maxima, you'd have to load these packages. In some installations, they are loaded by default. So a key thing to note here is there are plenty of probability distributions, and they all have certain properties. You know, they have probability density functions, they have a quantile function, they have random generation, and so forth. As far as Maxima is concerned, if you start the name of a distribution with PDF underscore, it is going to give us the probability density function of whatever name you specify. If you start with CDF, it is going to give us the cumulative distribution function of whatever name you specify. If you start with quantile underscore, it is going to give us the quantile function. Quantiles are simply percentiles. And if you start with random underscore, it will give you randomly generated numbers. From the specified distribution. So I'm going to pick the easiest one, which is a normal distribution. Of course, you can search through all sorts of distributions. There are gamma F distribution, Pareto distribution, Rayleigh distribution, and so forth. Normal distribution is something you guys know. So I'm going to start with the PDF. I forgot to close. So I could simply do PDF underscore normal, and that should give me the distribution. I'm looking for a value, so let me just say 0, and we have to specify the mean and the standard deviation, 9 and 1. Okay, so I'm just going to pick one single value, which is x, and I'm going to have 9 and 1. 9 is the mean, 1 is the standard deviation, and that is the corresponding value for that density. Now, if I want to generate a sequence of values, you can create a list of values, 0, 0.5, 0.2, 0.3, and evaluate the densities at each of those points, and that's what we would have. And if we don't want to have complicated expressions, we could always do float, and we'd have floating point values. These are the density values at x is equal to 0, x is equal to 0.5, x is equal to 0.2, x is equal to 0.3 from a normal density function with mean 9 and standard deviation 1. Now, CDF is simply the cumulative probability distribution function of a density. So, as I mentioned earlier, if it is a CDF, we've got to start with CDF underscore, and this is a normal distribution. And I'm going to pick the value 9 and mean of 9 and standard deviation of 9. Well, think about this. You have a normal distribution of mean 9, and I want to know the cumulative probability below 9. It better be 1/2, and it is 1/2. So if you have a mean of 9 and a standard deviation of 1, we know that the probability is going to be very, very small if you went past 3 standard deviations below the mean or 3 standard deviations above the mean. So I could pick, say, a value -10 and mean of 9, standard deviation of 1. I need to get a very, very small value, and that is the value that we get. I can convert it to a floating point number, and the probability is 0. So that is what we expected, and that's what we have. The next case is to generate random numbers from a normal distribution. So norm rand. If we want to generate random values from a distribution, we simply say random underscore normal. The syntax in R, I've got to mention that there are a lot of similarities between how Maxima does and Lisp does and what we have in R. As I said multiple times, that they are related. So the random normal in R would start with the number of observations. So I'm just going to go with the number of observations, which is 10 and 9 and 1. And I end up getting negative 16.022. The order is different, so the mean goes in the front, the standard deviation follows, and the last one would give us the number of random values that we have to generate. So in this case 10, if I put 1000, I will have 1000 values in norm underscore rand. And we all know how to do a histogram, so WX histogram of norm underscore rand, and we have a nice little bell-shaped density, and the mean is about 9, the standard deviation is about 1.